I think after the exam tomorrow, I'm probably just gonna have to hurry up. Probably just gonna have to hurry up to school. I schedule it like tomorrow, after tomorrow, after I take the exam, I'll have to go to the dentist.
Okay. But at least it's after the exam.
Yeah, I mean, they initially had a schedule for like tomorrow at noon, but like, you know what, I still gotta take that exam, so I'll just hold off to one.
Okay. All right, on the board, we have today's attendance question. This is to try to find the maximum value and minimum value of the two variable function on the line. The line is already being represented with a parametric equation, x equal to t, y equal to negative 2t. You can also convert it into a one variable function. Basically, since x equal to t, that's y equal to 2 minus 2x, because t equal to x, and then x between 0 and 1. So then there's the equation of the line indicated fundamental relation between x and y. And then you can plug in the x and y equation into the function f of x, y. So it's possible to reduce number variable already and then use the calculus method to find the maximum. Is you will find the critical point, then at a critical point, and also at the end of the interval, we should be able to find the maximum. So that's pretty much the method that we learned in section 8.1. So but if not, you can replace replace what we were working on so far. Reduce number of variables if possible, and find the derivative, and then set the derivative to. Try it yourself and see if you're able to identify max and mean. Our function f, just give him the variable part, it equal to x squared plus y squared. Okay, and then since it's on the line, x and y has this relation, so I would reduce the variable. So let's say y 2 minus 2x. And then you can basically have this 2 minus 2x. The function formula is changed because we're trying to look at the value of the function on the line. These two variable functions definitely have way more value than what's indicated on the line, but we're trying to focus on what was the function value on the line. So that's why we have this relation. Also, since t is between 0 and 1, and the x equal to t, so x also is between 0. So you're looking for a max and median on a closed interval. Based on what we're talking about, if you have a function that's differentiable, then you have this closed interval. Closed interval is naturally bounded. On the bounded region, closed interval, the maximum is guaranteed. So we definitely have the max value and minimum value. So all we have to do is try to find that you will find the derivative and then set the derivative equal to 0. Okay. That will allow you to find the x value. Depending on whether the x value is in the interval or not. So we can look at max and mean. So in general, the method for determining the max and mean eventually are based on comparison of the function values. You can have a list of the x value, and you calculate the y value for every x value on the list. For example, since we have a closed interval, the endpoint is definitely in the list 0 and 1. And then any point that you might be able to find by setting up the derivative 0 should be between 0 and 1. If it's not between 0 and 1, you don't have to consider it, and that there's also no deviation. So let's try to find the derivative and set the derivative to 0. And then say if you have any critical point that we find, and the critical point should be in here. If you're able to finish early, let me see. I know a lot of time. I feel like I've been explaining the practice question on my own, but maybe you can find it before I was able to finish the finish the discussion. Okay, let me see what we have so far. In the submitted answer, the two of you, one is correct, one is not, so you might want to double check.
I think the classroom's so empty.
Okay, so let's continue. The derivative of the function is equal to derivative of x squared is 2x. Derivative of this is also square, so because of power rule, we have 2 times 2 minus 2x. But then the inside function is this, the derivative inside function is -2. Like this. Let's try to combine terms, and this is 2x, 2 times -4. -4 times 2 is -8. And then -2 times -2 is then times 2 is +8, so there's a positive x. Okay, we're setting this equal to 0. This is really 8, 10x equal to 8. So x equal to 0.8. So the critical point is in the interval, so we have 0.8. So these are the 3 values. The endpoint of the interval 0 and 1, and also the critical point between 0. So if you plug in 0 to this, all right, x equal to 0, you're going to find a 4. On the other hand, if you plug in 1, that causes equal to 0. So that's still going to be 4. Right, and then one more number in the middle. That should be. So the 4, I'm not sure if that's max. I mean, that should be max. I mean, finish the other calculation. I can see the first derivative this, and then the second derivative will guarantee what we find. It's equal to 10. So the second derivative is positive. That means the function is concave up, and we're guaranteed a 200 minimum at the critical point. So the critical point 0.8 should provide the minimum, and this is actually the maximum. These two are the maximum. Not sure what was the minimum. You have to plug in 0.8 into your function to determine, and that should be everything. So 4 would be the maximum. The other one is the minimum, and then see all the answers so far. Okay. Brent, that's not right.
I'm sorry, like,
It should be 4, and let me try to make this fit.
I guess the scanner must have read the,
4 is the maximum.
okay, I think the scanner probably had the, I think the scanner probably picked up the wrong one.
Yeah, that's right.
I was holding it up while trying to figure out what the answer was, and like, and I guess the scanner must have picked up my paper card like in the wrong position.
Yes. So this should be 4/5. Right, so the answer should be this one. Maximum is 4, minimum is 4/5. So the correct answer should be A. If you accidentally put in the wrong one, feel free to change it. And scanner is still on. I mean, if you're listening, please change your answer. I see a few answer that was wrong. It's definitely those of you are online, because in the classroom I can tell the moment you raise your part, tell it's right. But if you're online, I can't tell unless I scan. Okay, the answer is A. Let's update your answer. I'm gonna turn on the scanner once everyone. Gabrielle, is that you? It should be A. Okay. So this is what we have so far. We have one student that hasn't changed it. Anyway, I'll leave it there, just in case you find out you had the wrong answer. We'll change it. Okay, today we're gonna try to prepare for tomorrow's exam. We're gonna have test due tomorrow. Do you have any question? Do you feel like we should talk about it before we do anything else? Do you have any questions? Anything you want to mention? Are you able to finish most of your homework? Okay, I was looking at section 12.9. I think half of the class is still not finished yet, so please try to catch up. I'm pretty sure most of you attending would know that the test is coming up. You probably are getting, like, still working on it or getting it finished. But I'm worried about those of you that are not in class the whole week. The whole week of last week. Any questions? Right, I didn't see any question in class. Those of you who attend online, do you have any questions? Okay, question 7 and 8, practice test. The solution is also there, but we can try to start from the beginning. 7 and 8. So question 7, try to find the critical point and then determine if the critical point have a relative maximum, minimum, or a saddle point. So let's see. So the process following closely what we were doing in section 8. Pretty much we're trying to follow like one question per section kind of thing when we design the exam. I try not to put too many exam on the test, too many questions on the test because sometimes people don't have enough time to finish, like trying to limit number of questions. Okay, so this is a two variable function. So therefore we have the partial derivative. Its derivative in the x variable equal to, you can see the x to the power 4, that's derivative for x cubed. First one goes 4x cubed. When you're differentiating the x variable, the y variable is a number. So y to the 4th has 0 derivative if its differentiation with respect to x. All right, in this one, the derivative of 4x, negative 4x is negative 4, but of course you have to multiply with y. In this case, the y multiplies as a coefficient. So that's negative 4y. So that's the partial derivative in the x variable. And then we can find the partial derivative in the y variable. It's a similar process. We have 4y cubed. Differentiating this one, the y differentiated with 1, so it's negative 4x. And that's what we see. Also, when you try to observe this function, the x force plus y force, and then there's an x times y. So in this original function, you can switch the x and y, like x become y, y become x. You're facing the same function. So the function has no change when you switch x and y. That means that x and y are symmetrical. And you can see from the derivative, they have very similar format, even though one is x and y. So we can almost imagine the critical point should have x equal to y. So that's what I observed. But we can definitely mathematically prove it. Now that we already find the derivative, in order to find the critical point, we would set the derivative to 0. So this equal to 0. 0. So we're working through the process, even though we're expecting x equal to 1. But if you're like short on time, you can just go ahead and assume x equal to y, and this will be like 4x cubed minus 4x equal to 0. You can solve the x value from that's a little bit quicker. But if we don't assume that, we can algebraically prove x equal to y. Now, the first equation will give you this. We divide both side equation by 4 and then move the y over. You're going to have y equal to x cubed. All right, and then you're going to burn that the second equation has a similar effect. So have divide both side by 4, move the x over, then x equal to y cubed. Okay, so everything is leading to the fact it seems to be symmetrical in the relation of x and y. So what do? We can, one thing we can do is we can multiply them or we can divide them. Let's see, we substitute, okay? So if we substitute y into the second equation, we end up having x is equal to y cubed and y equal to x cubed. That is x cubed equal to y and then cubed. We substitute it. So this is x equal to x to the power 9. Okay. And then you move the x over. You will have x minus x to the power 9 and do really basically try to ultimately solve the x value. And then the x is a common factor. You factor the x out, you have 1 minus x to the power 8. Which equal to 0, and because the factoring would reduce the number of variable in the equation, so x is a factor which could be equal to 0, or it's an OR relation, so you don't have to have both. So one of them, so you can consider that's case 1. This case, not case 2. X8 equal to 1 means x is an even power equal to 1, so x could be 1 or negative 1. So x equal to 1. Or x equal to negative. So after we're solving this, we realize that the consider that's like three case 1 and case 2, second, and then case 3. So why are we doing this? Because ultimately we have to find the x value and y value pair. If you determine the x value and then consequently that will affect the y value, every x corresponding to a y value. So different x value leading to different y value. So we're trying to separate the cases. So now we have 3 different scenarios that kind of indicated 3 point. If x equal to 0, now going back to the original relation, this has to be true. So y equal to x cubed, if x equal to 0, then according to the first case, y equal to 0. So the first point is 0, 0. And we're still at the age of determining the critical point. Determine all the critical points. And I'm going to look at all the critical points and the critical points they are. On case 2, if x equal to 1, y equal to x cubed, then y equal to 1 cubed, y equal to y equal to 1. The third case, x equal to negative 1 cubed, and then y is negative 1 as well. So then after we find out all the point, we realize it does show x equal to y at the critical point. See, 0, 0, 1, 1, negative 1, negative 1. We find 3 point. Now we're done. So this is and finish answering the first question, determine all the critical points. Second question is use the second derivative test to determine which case it is. Max, the mean, the set of points. So now I'm gonna try to make a table just so we can cover all 3 points. So I'm trying to make a 4x4 table. These are the points. So we got the first point goes 0, 0. Second point is 1, 1. Last point is negative 1, negative 1. We were supposed to do a second derivative test, so we have to calculate the d. And we also have to calculate the second derivative. That's what we're doing in the second derivative test. And it's kind of messy now, but the ultimate idea is solve the critical points, try to identify the case steps there. And then from there, we find these 3 points. 3 points is definitely absolutely necessary. All the middle part of the process of solving really is different from person to person. I mean, my personal style tends to be all over the place. All right, and then second part, we're going to try to calculate the d and calculate the second derivative. Now, to calculate second derivative, we have to get the second derivative function. Right, so we will have f(x)(x), which is differentiated from the first derivative. That's the only x term, so we get 12x. And then we have xxy. It's also calculated using f(x). There's only one y term. There's a square. I remember one time I forget the square when I was differentiating. So move the power to the front, power minus left. There's a square. And then the FYY. Getting ready to create a formula for D. FYY is calculated using FY. So this is 12y squared. Right, so that's there. And then let's calculate D. D equal to fxx times fyy, so second derivative, minus fxy squared. It's the secondary matrix of determinant, cross multiply, subtract. Think of it. Just trying to figure out a way it's possibly for us to remember how D is being defined. So it's equal to these two multiplied. So 12 times 12 is 144. So it's 144 x squared y squared minus the negative 4 squared is minus 16. Okay, so let's look at it. If it's the first point, 0, 0, so this will be 0. The D is negative 16. Whenever D is positive, we could find the max and mean. If D is negative, it's like it's a different scenario. So in this case, it doesn't really matter. If D is negative, we got a set of points. All right, and then if it's 1, 1, so 144 minus minus 16, what is that value? 128, which is positive, and then we find the first derivative. We plug in the answers, first derivative, the second derivative equal to 12. I guess I shouldn't call it that way. I should call it fxx or fyy since partial derivative. These are the first derivative notation, one variable notation. So it shouldn't be that notation. It's like this, one of these. So it's positive, so therefore it's concave up. So we have a minimum, like relative minimum at 0.11. And then the negative one, you put in the formula for D. Right, and that will still be positive 128. And then we enter into the second derivative, they're also positive. So those are also relative. We don't have a relative maximum point in that case. But that answers all scenario for all 3 points. Okay, it's easy to tell why this is the case because if x equal to 1, 1 or negative 1, negative 1, these are causing them to have the same answer. So negative 1 times negative 1 or 1 will be the same. So they have exactly the same value. If one of them is a minimum, of course, they have to be a minimum since they are the same value. And that's all the answer for question 7. And we can actually, I already have the solution here, and we're in that answer. It's different. So 0, 0, 1, 1. There's no negative 1 or unequitable 1. So at the beginning, it was the same. There's a negative.
It was just a negative 1. So, I was going to ask that, but when you saw it, we had a different one this time.
Right. So that the write-up was wrong. Y to the power 3, raised to the power 3. We were supposed to multiply the power, so it should be y to the power 9. The power 6 was wrong. Yeah, so this one, it's missing that part. So this is also substitution. We substitute x equal to y cubed into the first one, so it's y cubed to the cubed power. This is substituting x into the first equation. And what we did is substituting this into the second equation. But ultimately, it's the same thing. The power 3 of 3 is power 9. If you have x to the power 3 times x to the power 3, it will equal to x to the power 6. But if it's x to the power 3 raised to the power 3, the 3 times 3 is x to the power 9. Okay, so I guess this write-up was wrong. It should be positive 1 and negative 1. This should be y to the power a minus 1. So there should be two answers with y. So y equals 0 and y equals 1 and y equals negative 1. There should be three cases. So here in the write-up, I only find case 1 and case 2. There should be a one more point. I guess maybe that was the reason that you find a different answer. So it should be this the actual answer for it. That was a mistake. It's missing one point. That's the answer for question set 7. Sorry about my typo on the solution set. Let's talk about number 8. So those are the question. Number 8, if we look at the question by itself, it's this. Find the maximum value of x to the 4 is y to the 7 on the unit circle. I think it's one of the homework question. Okay. So this, you can do it with the Lagrange multiply method because the unit circle can be represented by equation. What's unit circle is a circle of radius 1. So it's x squared plus y squared equal to 1. So let's call that G. Okay, this is our F. So we are maximizing this function with this constraints. So according to Lagrange multiply method, the gradient of F should equal to lambda times the gradient of G. So this will give us two equations. These two equations together with the constraint equation, x squared plus y squared equal 1. Or how are we going to solve it? So the Lagrange multiply method will allow us to write a system equation. Solving the system equation, we'll find out exactly which x value and y value could possibly give us the maximum value. All right, and then the rest is a solving process. The gradient for f is, okay, so we find derivative in x, that would be 4x cubed y to the power 7. And then the gradient derivative in y would be 7y to the power 6. And we still have to multiply by x to the 4th. It equal to lambda times the gradient of g, that would be 2x 2y. So there's a relation between the gradient. So we change the system equation to a more specific relation. So the first relation is the equation goes 4x cubed y to the power 7 equal to lambda x. Second equation is a derivative y relation. 7y to the power 6 x to the power 4 equal to 2 lambda y. The last equation is x squared plus y squared equal to 1. That's the system equation that we were supposed to solve. Okay, so we do have to solve the variables. So let's look at this equation. I would say the first equation seems to be somehow relatable. I see the 2 lambda and then there's 2 lambda. So what come to mind will be, there's a lot of common factors that we can divide and cancel out. So if you take the first equation, divide by the second equation, equation 1, equation 2, and then equation 3. In solving part, equation 1 divided by equation 2 allows us to say some relation between x and y. So 4 over 7 x cubed over x to the 4. So we have x canceled. So the x is left with a denominator. Y to the 7 divided by y to the 6, we have a y in the numerator. So that is the division of the left side of equation 1 and equation 2. On the right side of equation 1 and equation 2, the 2 lambda cancel, we have x over y. Okay, and then that's what we have. And then you cross multiply, we say that 4y squared equal to 7x squared. Or we can simply say that the y squared equal to 7 over 4x squared. So why do we do this? Because we realize the equation, the third equation is relation between x squared, y squared. Now we also have relation between x squared and y squared. Maybe these two combined will allow us to solve x and y. So we substitute the y squared into the third equation, which will have x squared plus the 7/4 x squared equal 1. So 1 plus 7/4 is 11/7 x squared equal 1. So x squared equal to 7/11. And therefore y squared, since they add up to be a 1, y squared equal to 4/11. So after we find out x squared and y squared, they're all unit circles, so they can be positive or negative. That presented, if you had a unit circle, right, and then you have x squared, y squared, that gave you 4 points. Negative, positive x, negative, positive y, so that's 4 points. And what do we have? We're gonna have x equal to positive or negative 7/11, and y equal to positive or negative 4/11. Right, these are 4 points. You plug in those 4 points to say which one give us the maximum for this. Obviously, you guys square can immediately do this. So the x squared is 7/11. The x force is 7/11. And 7/11 is x squared. So x force is 7/11 squared. Now the y7, y to the 7th power, y squared is 4/11. So y6 power is 4/11 cubed. And then we have one more y, and then for the maximum, we will choose a positive y value. So we choose positive root 4. So multiply by root 4/11. That should be the maximum. You can simplify this to what was the power? It's the denominator is 11 to the power 5 half. Like the root is half power, right? 11 to the power 5.5. You are sure it will be 7 squared is 49 times so much. 47 to the power 2 times 4 to the power 3, and then times 2 is root 4 is 2. That's pretty much how we would solve it. And then question 8 is the process I did earlier. Similar procedure. So we find the x squared and y squared, there were 4/11, 7/11. Did it all the same? Okay. Maybe I did it wrong that time too. What was it? 4y squared times 7x squared. So these are the same. And then y squared. 7/4. So right, I don't see the difference. It's 7/4, y squared will be 7/4 x squared, and then 11 x squared will 4/11. Oh, right. Okay, so the denominator was 4. Somehow I switched it. So x squared, somehow for some reason I switched, so 7 is 4 in here. So it must be 7 over there. I'll actually change it to a 7. But the rest of them should be similar. So that means this is 4. That was 7. All right, in this case, you can check the calculation. This is a correct answer on the Newton. The posted answer was right. Right, when I was in the process when I was doing that fraction, I made a mistake. But this is pretty much the overall calculation steps. This answer should be saying that as you see over here. this is an answer. Any question? So I hope that answered your question. Yes, right. That's a good point. The name mistake. Yes, it was denomination before. Somehow when I add numerature, I somehow copy the wrong number in the denomination. Any other questions for the test? We pretty much went through the lengthy process explaining question 7 and 8. I felt like if you went through the calculation, you might find the solution easy enough to understand. I pretty much repeated what was sounding right up, except I didn't make the calculation mistake there. Y to the 3 to the power 3 is y to the 9. Any other questions? Any other questions? So if we try to briefly go through the rest of the test question, just to, we're gonna study guide, and you can also look at all the other assignment to practice similar scenario. The study guide for test 3 is, question 1 will be a partial derivative calculation, so it could be any of those multivariable functions. Find the partial derivative for it. It could be lower, like the degree 1 partial derivative, could also be a partial degree 2 partial derivative. There's a wide variety of questions in the homework. Find equation of the tangent line. This is going to be a 3-dimensional tangent line, so you might want to review how to determine equation of line. Determine equation of line, you need a vector that indicated direction and vector indicated the position of the line. Number 4 is understanding total differential, using total differential to approximate, or using total differential, or basically calculating the total differential. Number 4 is directional derivative and maximum rate of change. To remember that at the location for the maximum rate of change is a vector that is the same as a gradient vector. Number 5 is multivariable chain rule. So if you have several variables, some variable is in the first layer, some variable is in the second. So you have a function of x, y, and then x, y itself is a multivariable function. So you have a function inside the function. Chain rule applies to when you have composition function. Because we have multiple variables, then the multivariable chain rule, meaning that you have several variables involved. So one of the purposes of the multivariable chain rule is being able to do the differentiation easily, because the format will be simpler with a chain instead of without the chain. Number 6, simplification using multivariable chain rule. Number 7 is the question calculating the critical point when you have 2 variable function and classifying them as relative minimum, relative maximum, or set of point. Number 8 is a Lagrange multiplier method question. So it should be some of the homework from something like that. So I made an example of it. So it's not the actual test question, but it will be a similar format. The first question I have this, and you want to find the derivative. This is a first derivative calculation, but it could also be a second derivative calculation to make sure you're capable of doing the partial derivative calculation. Number 2 is find equation of tangent line. In this case, we already have a point. So what we need to do is to find the directional derivative. To find the derivative. And so if you have any difficulty, please let me know. Number 3 is try to find the total differential dv. So dv should equal to derivative of the v, so vx multiplied by dx plus vy multiplied by y. So you need to find out the partial derivative of v with respect to x, or partial derivative of v with respect to y. These are all the calculation components for the dv. And of course, this has a number, so x equals 1, y equals 1. That will allow you to find the value, and dx dy is also given. So that was one of the question number 3. And number 4 is the directional derivative calculation. The question did not say directional derivative, but it says, let's find the direction where the function decrease fast, biggest rate of change direction. Number 2 is to find the maximum rate of change of the function, which should be the magnitude of your gradient function at a given. There's a point. So try to think about the reasoning. Sometimes I have, we have students that they finish all the homework really quickly. So by the time we're talking about this question, we will be at a loss, like what exactly a rate of change with multivariable function? How do we find the direction of it? Realize this is related to the gradient of the function. Number 5 is using chain rule to find the derivative of the function with respect to one of the lower level variables. So u is a function of x, y, z, and then x, y, and z are functions of s or t or s and t. So this kind of function is that if you plug in x formula into the x, y formula into the y, and then z formula into the z, your function u are going to be really, really long, and therefore the partial derivative calculation are going to be really long as well. So difficulty is there. So applying chain rule can make the representation easier. To try to review some of our old video if you are like don't remember how to do it. So if you have notes of what you did when you were doing the homework, will be the best, because your homework is, to me, is the easiest to understand. If you've done your homework correctly, your calculation will definitely lead you to the direction. But if you don't take notes or don't have your homework notes, then it's time to review the textbook, the past recording of the class. Number 6 is calculating a partial derivative using the multivariable chain. So we would find the partial derivative of this function. The whole left side, you assign that into a capital F. So dv dx equal to negative fx over ft. That's the section 5 homework. Right. Next one is try to find this is the one that we already did together. So hopefully 7 and 8 was okay. Right. If you don't have any particular question, and I don't feel like I need to talk about anything, any other related test related question or homework related question? Any question? The main thing is make sure that you finish all the homework. Because if you don't do the homework, you don't have enough practice of the skill, or you don't have the fluency, then during the test, you feel like it takes forever to solve a problem, and you have to think on the spot, like how do we solve that type of problem. So make sure you have a plan for it. I do allow students to bring an index card as a testing aid. So on the index card, you may like try to briefly explain to yourself what's the main point for that type of question. So there's no question then, right? So let me go through a little bit more. 13.2. If there's nobody have any question left, without like at least half an hour left in the class time. So moving a little bit forward and chapter 13. Basically 13.1 focus on calculation of integration. So we review integration formula, talk about multivariable integration, iterated integration. So now 12.2, we're going to apply integration to do something, right? So what integration is good for? We actually already talked about one of the integration, which is calculating area. That when we are using integration to calculate area, that involve a lot of trying to analyze the area, the integration region. So you have to look at the area you want to calculate and figure out, does it have a numerical boundary horizontally or vertically? Does it have a variable boundary? So you have to identify the proper integration region when you are using double integral for area calculation. Now, 13.2. 13.2 is the second section of chapter 13. We're slowly moving forward, like now that we have double integral or triple integral, what can we do with the higher level integration? One of the things that we can do is to do volume calculation. So volume calculation and geometry volume is a big thing. The typical thing to think about is area is a two-dimensional calculation. So you often have to look at a two-dimensional region that you are studying and then try to find its upper boundary and the lower boundary, left boundary, and right boundary. That's two-dimensional. The volume is three-dimensional measure, so we have to look at all three dimensions. Sometimes we just call them the length, the width, and height. Okay, so and that make that a really good application for integration for higher level integration. So here we're gonna review the definite integral that we were talking about in calculus 1. When we are integrating a function from one number to a higher number, integration from a to b f of x dx, the main purpose for a definite integral is at the beginning, we're using definite integral to calculate area under the curve, area below between the curve and the x-axis. That's the integration ab f of x dx. Now the calculation part of it. We have the fundamental theorem of calculus. If we have the antiderivative of f of x, it's fb minus fa, if we have the antiderivative. But the process of understanding it is by Riemann sum. So in calculus 1, what we did, if you want to calculate area of the curve, what you would do is just dice up the integration region into intervals, small intervals. For example, if it's a to b, then you would divide up the a to b into n pieces, so that the entire region below the curve would become many little rectangles. The rectangle will be really, really thin, and an area of each rectangle is going to be the f of x representing the height, the delta of x representing the thickness of the rectangle or the width of the rectangle. So a rectangle's area can be calculated. Adding up all the rectangle is a approximation of the area below the curve. You take limit value of it, which will be a summation of the area below the curve. So that idea is the idea of Riemann sum. So here I'm using a little example to show that at the beginning you may have 1 interval, 2 interval, now it's 4 interval, 8 interval, 16 interval. So as n gets bigger and bigger, the interval get more and more detailed. The approximation of the area below the curve gets more and more accurate. And then here we have you can see the error gets smaller and smaller. In this, it's a little computerized graph showing the process of when n gets increased, the error is getting smaller, approximation gets more accurate. Anyway, so now let's talk about this two-dimensional functions, the volume calculation using integration of two-dimensional function. Now, suppose you got a surface, which is that curve that you see, the blue curve. The surface is a function v equal to f of x, y. So the height is a z value. And let's say we focus on the small piece. We're dicing this up into cubes. So all these are you dice it horizontally along the x-axis and also along the y-axis. That's why it become a little grid on the xy plane. Every grid is corresponding to a single bar. Here we're drawing this red bar. The height of the bar is a z value. Now the thickness is delta x times delta y. So the base area of the bar is a little square or a little rectangle. So if we want to calculate the volume of that bar, the red bar in the picture, then the delta x times delta y will be the length times width at the base. And then the f of xy is the height of the bar. That is one small volume, but we have to add it all together. There's many square. There's many little square at the bottom. There's where there could be many bar for the total volume under the curve. So you have to do a big summation. So we have to add so many. Now, this summation, when n goes to infinity, this summation is the double integral that we had. So then you can think of the volume calculation as a signed volume because the f of x can be positive or negative. If f of x is positive, then this volume will be a positive volume. Now, if the function f of x is negative v value, so you will have negative value of fxy, but the positive value for dA. Now, here we have dA instead of dxey or dy dx because we are not sure about the integration order, the order of the integration. That's why a common way for volume calculation will be you have a double integral notation with r at the bottom, and then you have your function, and then you would write dA because dA indicating that you could be doing dxey, or you can do dy dx. That's a short version of giving us the freedom to determine whichever order of operation that's easiest for calculation. That's why we have dA. dA is the same as dxey or dy dx, but also make it more general. Okay, of course, it also follows the idea of the Riemann sum. So this is the sign volume of V under F is the double integral fx dA. Let's talk about the order of operation. Well, we already mentioned it in section 1 that dxey or dy dx, they should be both are okay, but it depends on what is the proper boundary for your integration region. So let's say R is a closed bounded region and V is a function that's a continuous function on the bounded region defined on the region R. So if R is bounded by a numerical region for X, but a variable region for Y, then the proper integration order will be dy dx. If R is bounded by a numerical region for Y, but variable region for X, then the better way for calculation will be dxy. But both of them should provide the same if you can do both. This so-called Fubini theorem. And so the order of operation can be adjusted based on the integration region. All right, let's look at a exercise question about the volume calculation. Basically, it's thinking about the in this question, we're really looking at the f of xy as the value, the height. Okay, so we're looking at region below it, but the orientation can be changed. You could be finding the area to the left of a certain curve, or in front of a certain curve. So the base, the bottom region in this question is the xy plane, because we use xy as our as our independent variable in the two variable function. You could also have fxz and then x times z plus e to z. So the variable can change, the orientation can change. But since the change of variable is possible, so we focus on the two variable function using xy as orientation. All right, this question says we have a function defined as x times y plus e to the y. The picture is already here in the book. We want to find the sign volume under F on the region R, which is the rectangle is corner 3, 1. 3, 1 is over here, and the corner 4, 2, which is over there. So it's basically a rectangle region, a rectangle integration region, which is good because rectangle region means we have numerical boundary for X and numerical boundary for Y. That means we have the freedom to use any of the order of operation. Okay. Let's look at the calculation. Now, how do we calculate? Initially, we're integrating x and y plus ey dA because the integration order had not been decided. We don't know, are we doing dy dx? Are we doing dx dy? The answer is because the integration region is a rectangle, we can do it either way. Both are okay. So let's look at the calculation. In the textbook, we were presented the both of the integration order. For example, you can do dy dx or you can do dx dy. I took some time to write up the calculation, so you don't have to look at my awful writing speed. All right, so let's say we do dy dx, meaning that we are making the x as the outer layer and the y as the inner layer. So there's a they are like the wrap of things. So if you have dx as the outer layer, then the integration region integration boundary 3 to 4 will be the boundary for the x value, right? dy is the inner layer, so the second integration boundary is 1 to 2, the 1 to 2, value. So number one thing is you want to write it out in the way that the integration boundary is set up the right way. Because if you ever switch them, if you accidentally put 1, 2 and 3, 4 instead of 3, 4, 1, 2, then you are having the wrong boundary for y and x. A very, very small mistake can cause the calculation to be all different. Make sure you have the right order. Dx on the outside, so this is the boundary for the x value 3 to 4, dy, and then 1 to 2 for the boundary for y. Okay, so that's all set up, and then the rest is all calculation. We will follow what we had in 13.1, which is iterated integration. Iterated integration meaning that you gotta finish the inner layer and then move on to the outer layer of integration. So here we are. So number one, we're gonna try to finish how we integrate xy plus e to y dy. If you're integrating dy, then antiderivative of integration of ey is e to the y, and then integration of y, you have y squared over 2. So that you can see the x is multiplied factor, x is coefficient. So that's the antiderivative, and I'm gonna put in number. Now the function is so right now the antiderivative has x and y, so I try to indicate that here is integration dy. So the 1 and 2 are initial y value and terminal y value. Make sure you're replacing y equal to 2, y equal to 1. Just so we're not replacing x by 1 and 2, we're just trying to make sure that we're not off track or accidentally we're using the wrong number. And then I'm gonna plug in the number. So plug in y equal to 2. So we have 2x plus e to the 2. Plug in y equal to 1, and we have x over 2 plus y plus e to the 1. And upper limit value minus lower limit value, applying the fundamental theorem of calculus. Now we're done. We're done with the inner layer of integration. Move on to the integration outer layer. If you integrate 2x, you have x squared. But what I did is 2x minus x over 2 is 3 over 2x. 3 over 2x integrated, we have this. 3 over 2x integrated as 3 over 2 times x over x squared over 2. E to the power 2 minus e to the power 1 integrated is e to the power 2 minus e to the power x. And we're going to plug in x equal to 4 and x equal to 3. That's our final answer. So this is if you write it out, the entire calculation, what you see. And you can compare that with the textbook solution. This is a much more well-written solution, but I'm trying to present it in a step-by-step manner. The final answer is 9.92. Any question? Okay. All right, so of course, we can also change up the order of the integration to dx dy. And this is how we do it in dx dy. So if we do a dx dy, that means that the inner layer will be 3 to 4. And then dy on the outside, so the y will be from 1 to 2. As you're integrating the inside xy, integrating the x squared over 2, integrating the ey, it will be ey times x because the e to the y will be a number. And then we plug in 3 and 4, and we will find the antiderivative. Integrate the y, we'll have y squared over 2. Integrate e to the y, plugging upper limit, lower limit, you will be getting the same answer. So either method actually presents a different process, but the final number will be the same. All right, let's get one more example. A second example on using double integral to find volume. Oh, it's a volume calculation already, already into, we're evaluating a double integral of 3xy minus x squared minus y squared plus 6dA. Now, what's the integration region? Integration region R is a triangle bounded by x equal to 0, y equal to 0, and x over 2 plus 1. So it's a triangle over here, x-axis, y-axis, and then a line that forming this little triangle. So that's at the base on the XY plane, you can see the base of the shape. And then on the surface up there, you have a surface. This calculation will calculate the volume under this surface, which should be positive. So here are the calculation. And what we, you can do it both ways. Because we are a triangular integration region, you can do it dy dx, or you can do it dy dx dy. If we're doing dy dx, then you have to have x in numerical boundary. The x is from 0 to 2. Now the y would have a lower boundary, upper boundary, because y is low to high. So the lower boundary for the y value is at 0. Upper boundary is on this line. Now, if you want to identify the proper integration region, you have to solve for the x, solve for the y value. I mean, dy, right? Find the y. So in this equation, you find the y equal to 1 minus x over 2. So that's what we have. And as you try to determine the integration limit, there's nothing to do with the integration function. You can see with all this exercise, the integration function stay the same no matter how you do it. What is changing is the integration limit as you're changing your integration order. So as you switch the order of the integration, only the integration limit will be changed, will be adjusted, but there's no change in the middle. So we will differentiate, we'll integrate with respect to the y variable first. So 6 becomes 6y, y squared becomes y cubed over 3, x squared. X squared is dy, so x squared times y, because x squared is a number. A number integrated is all you have to do is multiply the variable. This y integrated y squared over 2, and we plug in upper limit and lower limit. This process and the textbook is being shortened. The process is so probably a lot longer than this. Yeah, there's a lot of simplification from this step to this step. There's a lot of jump. We skip quite a few steps from here to here. The substitution takes some time to do. So the term are already, this is after the term has already been combined and simplified, and you have this, and then we apply power rule to integrate. And after the integration, plug in x equal to 2, we have our final answer. So that's the solution number 1, using the order of operation dy dx. Same way, because the triangular integration region, you can also do the x dy. If you're doing the x dy, then the y will be numerical. You can see from the picture, y is from 0 to 1. So on the outside of dy, I have a boundary of 0 to 1. On the inside is the x. We have to find the left boundary and right boundary for dx. And from the picture of the triangle, you can see the lower boundary for x equal to 0. The upper boundary for x is on this line. You have to solve for the x value in the equation. So I guess we move the y over 1 minus y. You multiply both sides of the equation by 2, so it's 2 minus 2y. 2 minus 2y is the upper value for the x. So there's a certain solving process when you try to adjust the integration region. Again, there's no change to the integration function. The process did change. You have to integrate the x. So here we have 6x, and then that's y squared dy, and then that would be y squared times x. Using power rule for integration on the x variable, we plug in x equal to the upper boundary. And again, this process has some simplification. After combining term and simplify, we have this power function. Applying power rule, integrate the y variable, we will be arriving at the same final answer. The process could be a lot more tedious than what I'm explaining. Other than more time consuming, there's no new stuff in here. All it is trying to avoid calculation errors as we were combining terms, simplifying terms. Any question? So this is using double integral for volume calculation. All right, so one of the things you already noticed that as we were doing the double integration using the iterated integral, the limit in the integration limit or the bounds of the integration depend only on the integration region R. So it doesn't affect the function f. The integration function does not change. And then the integration function does not determine the bounded integration region. Whatever it is, that's what you have to pick for your integration limit. Okay, a couple of property about the double integral. Many of the property that was true for a single integration is still applies. For example, if you have a common factor that is constant, not related to any variable, this number can be factored outside the integration. Just so your integration function will be a little bit shorter, a little bit easier follow through. Number two, if you have summation of two functions that you need to integrate, then you can integrate each function by itself and then add it or subtract it later. So that's the second rule, which could be possibly make your integration a little easier to do. Number three, many of these properties are in the hope that the calculation will be more simplified or streamlined. Number three, if you have a positive function, then integration of positive function will be positive. And that's also true in type 1. If you have a single function that is positive, integration of positive function is positive. Number 4 says if one function is bigger than the other function, then the integration of the same integration region of the first function will be bigger than the integration of the smaller function. Number 5 says if the integration region can be partitioned into two parts, then the integration can be calculated by integration of the first part plus integration of the second part. Assuming these two regions are not overlapping partitions. Right, so these are 5 rules that occasionally will be helpful when we're doing calculation, allows us to do a calculation on smaller ranges. And smaller values, smaller calculation. Right, for example, so here we have f of x equal to sin x cosine y. The integration region is a triangular region formed by -1, 0, 1, 0. So they're on the opposite side of the origin on the x-axis and 0, 1. So it's going to be a isosceles triangle. Evaluate the double integral fx by RBA. In this one, I kind of put all the calculation here. All right, so maybe we can do it without looking at the solution. Let's try to do it ourselves. Right, see if that's the question, then let's look at the integration region. If you are just look at the problem itself, look like this, right? So if the question looks like this, meaning that the integration limit is not given, you have to determine for yourself. The integration order is not determined, you got a dA, so you have to determine, in that case, do I do dx dy or dy dx? So I have to think about what will be the best way to do it. It really, how you determine your order of integration, it depends on the integration region. The region R is which side will be better. Here are the 3 points. The first point is -1, 0. Second point is 1, 0, which is like here. Last point is 0, 1 here. So we got an integration region like this. Okay. So if there's our integration region. So if we think about it, the y value, or where does the y value is going to be y value is from 0 to 1. Okay, so y value is 0 to 1. What about the x value? The x value from this to this. So it looks like the y value is not a single. The y value actually, you can also say the y value is from here to here or from here to here. And these two are not consistently the same boundary for the y value. So if you think about the best way is to make sure the y value is numerical boundary and the x value is variable boundary left or right. The boundary on this side is this and that side is that. It's pretty clear. So in this case, a better option will be we should do dx dy. Dx dy. The reason for that is you can see that we tell the y value are from 0 to 1. On the x value, it's the left side to the right side. What are these lines? These lines can be represented by that was 0, 1. So definitely it's a y-intercept, it's a 1. Slope is, this is a 1, this is 1, slope equal to 1, so it's y equal to x plus 1. Okay. On this side, the slope is -1, so y equal to negative x plus 1. So we can quickly identify mx plus b. The b equal to 1 because the y-intercept equal to 1. The slope is -1 and +1, so we can write these two. However, when you're trying to determine your integration boundary, what you're looking at is x value equal to this and x value that at the lower boundary, the x value equal to, going to solve for the x value, x equal to y minus 1. So the lower boundary is y minus 1. On the upper boundary, which is here in that equation, you have to solve for your x value. You bring the x over. It will be this x over and this y is over. So x equal to 1 minus y. That's the upper boundary. So it's 1 minus y. Any question? Are you okay? What I need to explain is how we exactly get to write the integration boundary. And then we're all set for calculation. The integration function is sin x times cosine y. Right, so that's what we're integrating. Kind of set it up so it's less time consuming. I wish to cover more material in single class, but also do not want to make it too fast that we're forced to rewrite it in the book ourselves. So that's our integration limit, and we decided to do dx dy because it's easier. If you have dy dx, then the x is 0 to -1 to 0, and then 0 to 1. You have to do two separate integration. So it's definitely easier this way. Okay, as far as the process of integration, we would do the inner layer of the integration is the first thing we have to do. And if you are doing dx, then the sin x is what we're integrating. The cosine y will be a variable, a factor outside. So you'll be having cosine y a little bit outside the integration. Integration of the sin x is negative cosine x. Negative cosine x has representative sin x. And then we put in the integration limit that has x equal to 1 minus 1. And then x equal to minus x. Okay, so this is the integration of the inner layer of it. Putting the upper limit and lower limit, we will have cosine y, and you have negative cosine 1 minus y minus negative, which is positive cosine y minus 1. There. So if you enter the upper limit and lower limit value for cosine, this is what we have. And I realize these are the same. Cosine is a even function. So cosine y minus 1 and cosine 1 minus y equal the same thing. And so there's a negative of this and there's a positive this equal. If the inner layer of the integration equal to 0, then the whole thing equal to 0. Let me look at the actual solution. So it is 0. Because these two are opposite of each other, so the final answer for the integration. Right, this also brings back one of the old saying that if your integration region is symmetrical, in this case, is symmetrical about the x-axis, and then we're integrating sine x, x is an odd function, integration of the odd function on the symmetrical integration region is equal to 0. Integration of an even function on the symmetrical integration region is double the half of the integration. So this one is interesting, that integration region itself is symmetrical. Right, looks like we're out of time. And I mean, this is not the main focus for today. I still hope that you guys will finish all your chapter 12 homework, so you'll be ready for tomorrow. Okay, I'll see you tomorrow. Get ready. Remember, you can bring your paper homework for extra credit. You can also use a index card for formula sheet, and also use your calculator if you want one. You can prefer using your calculator. I'll see you tomorrow. Thank you.
I had emailed you about testing. Can I just show you my home?
Okay.
And then, will they know that I can use the index card?
Yes, when I submit the exam to them, I'll attach, we indicate out there.
Okay, and then, thank you very much. I'll, schedule it out.
Already scheduled, please.
Not yet, no, I've never used it before.
Okay, do you know how to do it?
I can figure it out.
So if I have time, if you go to our website under academic, there's right there, the testing center. You click on testing center, and the middle of this one, schedule exam. And you can choose the alternate state exam. Nice class. These are all the instructions. Then you need to log in. The login is this.
Thank you very much.
Yes, it looks like you did finish all your homework. I saw your submission of it. So you're not coming here tomorrow?
Yeah.
Instead, you're gonna take it.
Yeah, when I schedule it, yeah. Thank you very much.
You ready?